Alright, let's get after it. Last class we did heating loads, and if you remember one thing from that class, it was probably this. Heating in this part of the world is the warm-up act. Today we get to the headliner. In Texas, the cooling load is the load. It sizes the equipment, it drives the utility bill, it dictates the size of the electrical service, and when it's done wrong, it's the thing the owner complains about every single August for the next 30 years. And here's why this matters to you specifically. You construction managers, not the engineers. You're not going to run these calculations for a living. A mechanical engineer stamps the design, but you will price the equipment that comes out of these calculations. You'll coordinate the duct that carries this air. You'll fight for the roof space and the ceiling cavity this equipment demands. You'll review the submittal where the contractor proposes swapping the specified unit for an equal. And you'll be standing there when the owner asks why the corner conference room is a sauna at 3 p.m. If you don't understand where the tonnage comes from, you can't do any of those jobs well. Today you learn where the tonnage comes from. Quick housekeeping. Daily quiz on last class, heating loads, is open now, knock it out. Today's participation assignment posts after class. I'll walk you through it in detail before you leave, and there's a load calculation worksheet attached to it, so stay to the end. Let's orient. Last class, heating loads. The core of heating is honestly pretty simple. It's cold outside, warm inside, and heat leaks out through the envelope at a rate driven by the temperature difference. Mostly steady state. One dominant driver, delta T, and the worst case happens on the coldest night of the year, when, conveniently, there's no sun to complicate anything and the building's probably empty. Cooling is a different animal, and this slide lays out why. For reasons cooling is harder than heating, and I want all four in your notes. First, the sun. Heating's worst case is at night. Cooling's worst case has the sun beating on the roof and blasting through the glass. Solar gain is a massive load that heating calcs never deal with. Second, the load moves around during the day. East glass loads up in the morning, west glass in the afternoon. The roof peaks mid-afternoon. Cooling loads are time-of-day dynamic. The peak isn't just how hot is it, it's how hot, at what hour, hitting which face of the building. Third, people, lights, and equipment. Every warm body, every light fixture, every computer in the building is a little heater running inside the space. In winter, those gains help you, free heat. In summer, they're load, and in a packed office or a classroom like this one, they can be the biggest load. Fourth, and this is the one heating never has to think about, moisture. Cooling isn't just about temperature, it's about humidity. Half the job of an air conditioner in a Texas summer is wringing water out of the air, and that work costs capacity. Which brings us to the single most important concept of the day. Quiz alert. 4 reasons cooling loads are more complex than heating loads. Solar gain, time of day variation, internal gains, people/lights/equipment, and moisture, latent load. Heating is mostly steady-state delta T. Cooling is dynamic. If you learn one vocabulary distinction today, it's this one, because everything else in HVAC hangs off it. Sensible heat versus latent heat. Sensible heat is heat you can sense, heat that changes the temperature of the air. Thermometer goes up, that's sensible. The sun on the roof, heat conducting through the wall, the warmth off a light fixture, sensible. Latent heat is hidden heat, heat tied up in moisture in the air. It doesn't move the thermometer, it moves the humidity. Every pound of water vapor floating in the air carries a load of energy with it. And to condense that vapor back into liquid water, which is exactly what your AC coil does, the equipment has to pull that energy out. People exhaling and sweating add latent heat. Outdoor air in a Gulf humidity climate hauls in enormous latent heat. Showers, cooking, coffee pots, latent. And the total cooling load is always the two together. Total load equals sensible plus latent. Your equipment has to handle both at the same time. Quiz alert. Sensible heat changes air temperature. Latent heat is the energy in moisture, humidity. Total cooling load equals sensible plus latent. If the quiz asks, which type of load do occupants add? The answer is both. Here's the physical picture that makes latent heat click. Go look at the condensate line on any rooftop unit or the drain pan under any air handler in August. Water pouring out of it, gallons and gallons a day. Where did that water come from? Out of the air. And every drop represents energy the machine had to spend condensing vapor to liquid, capacity that did not go toward lowering the temperature. That drain line is the latent load, made visible. Now, why should a construction manager care about the split and not just the total? 3 field reasons. 1. Comfort complaints. A space can sit at exactly 74 degrees and still feel swampy and miserable if the humidity is high. It's cool, but it's clammy, is a latent load problem, and it usually traces back to equipment that has plenty of sensible capacity but was never given the runtime or the coil conditions to dehumidify. Hold that thought. It comes back with a vengeance when we talk about oversizing. 2. Reading equipment schedules. Look at any mechanical schedule and you'll see the unit's total capacity and its sensible capacity listed separately, and their ratio, the sensible heat ratio, sensible over total. A unit with 60,000 BTUs per hour total and 45,000 sensible has a sensible heat ratio of 0.75, meaning a quarter of its muscle is budgeted for wringing out moisture. In a dry climate, you'd pick a high ratio unit. On the Gulf Coast, lower. 2. 5-ton. Units are not interchangeable if their splits are different. And that's exactly the kind of thing that hides inside an or equal submittal. 3. Certain building types are latent monsters. Natatoriums, locker rooms, commercial kitchens, churches and theaters that pack hundreds of people into one room. Anything with big outdoor air requirements. If you're managing one of those and the mechanical scope looks suspiciously cheap, the latent load is the first place to look for what got missed. The bookkeeping term for all this, the study of air and moisture mixtures, is psychrometrics. Engineers live on the psychrometric chart. You don't need to master the chart in this course. You need to know it exists. Know that grains of moisture is how engineers count water and air, 7,000 grains to a pound. And know that when the mechanical engineer starts talking wet bulb temperature, they're talking about the latent side of the problem. Dry bulb is the regular thermometer temperature, the sensible side. Wet bulb bundles in the moisture. Quiz alert. Dry bulb temperature equals ordinary air temperature, sensible side. Wet bulb accounts for moisture, latent side. Psychrometrics equals the study of air, moisture mixtures. Quick drill, call and response. 3 minutes. Let's drill it before we move, because the quiz will make you sort loads, and I want this automatic. I call out a heat source. You call back sensible, latent, or both. Ready. Sun beating on the roof. Sensible. Pure temperature, no moisture. A packed church congregation? Both. Bodies always give both. Skin heat sensible, breath and sweat latent. 100 LED light fixtures? Sensible. Lights make heat, not moisture. Outdoor air pulled in on a muggy August afternoon? Both. And heavy on the latent, which is the whole Gulf Coast problem. A pot of water boiling in a break room? Latent, mostly. It's pumping vapor straight into the air. A row of computer servers? Sensible. Electronics are dry heat. All watts, no water. Which, file this away, is why data center cooling is a completely different design problem than comfort cooling. An open door to the loading dock in July. Both. That's infiltration, and infiltration carries whatever the outside air carries. Good. If you can sort any source into its bucket like that, you've got the vocabulary. Now let's start counting the BTUs. Now we start building the load, piece by piece, the same way an engineer does. First bucket, heat coming in from outside through the building envelope, roof, walls, and glass, by conduction. The workhorse equation looks exactly like the one from heating class, just pointed the other direction. Q equals U times A times delta TQ is the heat flow in BTUs per hour. A is the area of the surface in square feet. Delta T is the temperature difference across it. And U is the U factor, the conductance of the assembly, how willingly heat moves through it. And remember the relationship you already know. U is the reciprocal of R. U equals 1 over R. R value measures resistance to heat flow. Bigger is better. That's the number on the insulation bag. U measures how much gets through, smaller is better. An R20 wall has a U of 1 over 20, 0.05. Double the R, have the U, have the heat gained through that assembly. Same equation, same logic as heating. Quiz alert. Q equals U times A times delta T for conduction gain. U equals 1/R. Higher R equals lower U equals less heat gain. If the quiz hands you an R value, flip it to U before you multiply. And here's where cooling gets its own personality. For cooling, the simple delta T lies to U on sunny surfaces. Think about a dark roof in July. Air temperature, 98. Touch that roof. You can't. It's 150 plus. The sun has driven the surface way past air temperature. So the real temperature difference pushing heat into the building isn't inside to air, it's inside to a solar-baked surface. And there's a time lag. Mass soaks up heat all morning and releases it into the space hours later. Engineers handle this with an adjusted temperature difference. The method on the slide is CLTD, the cooling load temperature difference. Instead of the plain delta T, you look up a CLTD value from tables that bake in the solar heating and the thermal lag, based on the surface type, its orientation, its color, and the hour of day. Same Q equals U times A times delta T structure, smarter delta T. That's the whole trick. A roof might carry a CLTD of 40, 50, 60 degrees at peak while the plain air-to-air difference is only 20, which tells you the sun can be doing 2/3 of the work. Run one on the board so it's concrete. A 10,000 square foot roof, insulated to R25, so U is 1 over 25, 0.04. Plain air-to-air delta T, 95 outside against 75 inside, 20 degrees. Naive math, 0.04 times 10,000 times 20, 8,000 BTUs per hour. Now use a peak afternoon CLTD of 55 for that dark roof. 0.04 times 10,000 times 55, 22,000 BTUs per hour. Nearly triple, same roof, same afternoon. The difference is the sun, properly accounted for. And run the fix while we're here. Upgrade to R40 and U drops to 0.025. The same 55-degree CLTD now yields 13,750. The insulation just erased 8,000 plus BTUs per hour, which, hold the thought until the tons slide, is most of a ton of installed equipment every year of the building's life, bought once at the roof deck. Quiz alert, CLTD equals cooling load temperature difference, an adjusted delta T from tables that accounts for solar heating of the surface and thermal lag. It's why a roof's effective delta T is far bigger than the simple indoor-outdoor difference. What does the CM take from this? Priorities. On a 1- or 2-story building, the roof is the envelope's biggest cooling surface and usually its biggest conduction gain, which is why roof insulation levels and even roof color are energy code battlegrounds, and why a value engineering proposal to thin the roof insulation is never free. It shows back up as tonnage and utility bills. Walls matter less per square foot than students expect. And glass. Glass is such a special case that it gets its own slide, which is where we're headed. Glass. Pound for pound, square foot for square foot, glass is the most powerful load maker on the building. A wall conducts heat. A window conducts heat and transmits solar radiation straight into the space, where it lands on the floor and the furniture and becomes load immediately. 1 square foot of unshaded west glass on a summer afternoon can emit more heat than 10 square feet of insulated wall. 2 numbers describe a piece of glazing, and you need to keep them straight because they show up on every window schedule and every energy code checklist. The U factor of the glass, same meaning as before, conduction. How fast heat leaks through because it's hot outside. And the SHGC, the solar heat gain coefficient. That's the fraction of the solar energy hitting the glass that makes it into the space. It runs from 0 to 1. An SHGC of 0.40 means 40% of the sun striking that window comes inside as heat. Lower SHGC, less solar gain. Modern low-E coatings are precisely engineered to knock the SHGC down, reflecting the infrared, while still letting visible light through, so the space isn't a cave. Quiz alert. SHGC equals solar heat gain coefficient, the fraction of solar energy striking the glass that enters the space, from 0 to 1. Lower is better for cooling. U factor covers conduction. SHGC covers solar. Two different jobs, two different numbers. Now orientation. This is my favorite part of this topic because it's pure geometry and it explains so much of what you see in real buildings. North glass. Almost no direct sun, just diffuse skylight. The gentle side. East glass. Hammered in the morning, done by noon. South glass. And this surprises people. In summer, the sun rides high at midday, so it strikes south glass at a steep, glancing angle and much of it bounces off. South glass is also the easiest to shade. A modest horizontal overhang kills the high summer sun and still lets the low winter sun in. South is the designable orientation. West glass is the villain. Afternoon sun comes in low and flat, straight through the glass at nearly 90 degrees. No overhang can block a low sun angle, and it arrives at the exact same hours as the peak outdoor air temperature. Late afternoon sun plus 100-degree air, stacked. That's why the building's peak cooling load so often lands between about 3 and 5 p.m., and why the west-facing conference room is the space that generates the hot room complaint in every office building in Texas. Quiz alert. West-facing glass is the worst for summer cooling, low afternoon sun angle, unshadable by overhangs, and it coincides with peak outdoor temperature. South glass is high angle in summer and easy to shade with overhangs. Building peak cooling load typically hits mid to late afternoon. The toolbox for taming glass, roughly in order of effectiveness. Less glass on the west in the first place. An architecture decision made long before you mobilize. Better glass. Low E, lower SHGC. External shading, overhangs, fins, screens, because shade outside the glass stops the heat before it enters, while interior blinds only catch it after it's already inside. And finally, orientation itself, which is free on day one of design and unfixable forever after. Where the CM lives in this. The window package is a perennial value engineering target, and swapping specified glazing for something cheaper almost always means a higher SHGC. That heat has to go somewhere. It goes into the load, and the load goes into equipment that was sized for the specified glass. If a glazing substitution moves the SHGC materially, the mechanical engineer needs to know before anyone signs anything. That's a coordination flag you now know to raise, and most CMs don't. Everything's so far attacked from outside. Now turn around. Some of the biggest cooling loads are generated inside the building, and in a modern office or a classroom, internal gains can outweigh the entire envelope. 3 sources: people, lights, plug loads. People first. Every human body is a little furnace running around the clock at roughly 98.6, dumping heat into the room, and dumping it in both flavors. Sensible heat off your skin, warming the air. Latent heat in your breath and your sweat, loading the air with moisture. The slide's planning numbers for a seated, office-type occupant. On the order of 250 BTUs per hour sensible and 200 BTUs per hour latent. Roughly 450 BTUs per hour total per person. And that's seated office work. Get people moving, retail, light assembly, and it climbs. A gym full of people working hard can be double or more per person, most of the increase latent, because working bodies sweat. Quiz alert. A seated occupant adds roughly 250 BTUs per hour sensible plus 200 BTUs per hour latent is almost equal to 450 BTUs per hour total. People are the classic, both sensible and latent load. Activity level raises it, mostly on the latent side. Run the room we're sitting in. 40 people at 450 is 18,000 BTUs per hour. And hold on to that number, because in a couple of slides you'll be able to translate it into equipment. It's 1.5 tons of air conditioning, just for the bodies. This is why theaters, churches, lecture halls, and courtrooms are sized around occupancy above all. The people are the load. Lights second. Here's the fact students resist. Every watt of lighting power ends up as heat in the space. Every single one. The light hits the walls and the floor, gets absorbed, becomes heat. There's no exception. A watt in is a BTU out. And the conversion constant is one you will use for the rest of this course. 1 watt equals 3.412 BTUs per hour. Quiz alert. 1 watt equals 3.412 BTUs per hour. All lighting wattage becomes heat gain in the space. Memorize 3.412. It converts any electrical load to a cooling load, and it will be on the quiz. So the calc is dead simple. Lighting watts times 3.412. Engineers usually carry it as a power density, watts per square foot. A modern LED office at around 1 watt per square foot. 10,000 square feet is 10,000 watts, times 3.412, about 34,000 BTUs per hour from lighting alone. And here's the good news story of the last 2 decades. The old fluorescent era ran 2-3 watts a foot. The LED revolution didn't just cut lighting bills, it cut cooling loads in every building it touched, which is why lighting retrofits sometimes let you downsize replacement HVAC equipment. 2 line items on your estimate, connected by 3.412. Equipment, plug loads, third. Computers, monitors, copiers, coffee makers, refrigerators, servers. Same physics, same constant. Nameplate watts to BTUs at 3.412. With a caveat, equipment rarely draws nameplate continuously, so engineers apply usage and diversity factors rather than adding up every label in the building. Typical offices carry another watt or so per square foot for plug loads. And then there are the special cases that eat buildings, server rooms, and IT closets. A single loaded server rack can throw off heat around the clock like a small car engine idling in the room, which is why IT rooms get their own dedicated cooling, why that little split system serving the MDF room is on the drawings, and why, when the owner casually mentions during build-out that we're adding a few more racks, your mechanical scope just changed. One more concept ties the 3 together: diversity. Not everything peaks at once. The full lighting load, every person at their desk, every machine running. That perfect storm rarely happens simultaneously, so engineers apply diversity factors instead of stacking worst on worst on worst. Remember that word. It comes back when we talk about why the whole building's tonnage is less than the sum of the rooms. Last load bucket. And in a humid climate, it's often the sneaky biggest one: outdoor air. Outdoor air gets into your building 2 ways. Infiltration, the uninvited air, leaking through cracks, joints, and every door that opens. And ventilation, the invited air, outdoor air you deliberately bring in through the mechanical system because codes and basic human health require it. People need fresh air. The standard that governs how much is ASHRAE 62.1 for commercial buildings, and it sets minimum outdoor air rates based on occupancy and floor area. Think on the order of 15 to 20 CFM per person for typical office-type occupancies once you run the numbers. Quiz alert. ASHRAE 62.1 is the ventilation standard for commercial buildings. It sets the minimum outdoor air, in CFM, for occupant health. Ventilation is deliberate. Infiltration is leakage. Why is outdoor air such an expensive guest in July? Because every cubic foot you bring in arrives hot and humid, and you have to condition all of it, cool it down, and wring it out. Sensible load and latent load, and in Gulf humidity, the latent side of outdoor air is brutal. 2 formulas on this slide put numbers on it, and these are the last 2 constants you need today. For the sensible load of an airstream, Q sensible equals 1.08 times CFM times delta T. CFM is the airflow. Delta T is the temperature difference between outside and inside, and 1.08 is a constant that rolls up the density and specific heat of air. Bring in 1000 CFM on a 95-degree day with a 75-degree building. 1.08 times 1000 times 20. That's 21,600 BTUs per hour of sensible load. Nearly 2 tons, just to cool the fresh air before the sun or a single occupant does anything. And the latent side. Q latent equals 0.68 times CFM times delta grains, same CFM. Delta grains is the moisture difference between outdoor and indoor air, measured in grains of water per pound of dry air. Those grains from the psychrometrics discussion, 7,000 to the pound. On a muggy Texas day, outdoor air can carry 30, 40 plus more grains than your conditioned space. Same 1,000 CFM at a 35 grain difference. 0.68 times 1,000 times 35, about 23,800 BTUs per hour of latent load. Notice that number. The moisture load of the outdoor air just beat its temperature load. That's Gulf climate HVAC in one comparison. And it's why humid climate engineers obsess over outdoor air, energy recovery wheels, and dedicated outdoor air systems, while their Arizona counterparts barely think about grains at all. Quiz alert. Q sensible equals 1.08 times CFM times delta T. Q latent equals 0.68 times CFM times delta grains. Know both constants, 1.08 and 0.68, and know which is which. Given CFM and a delta T, you should be able to produce BTUs per hour on the quiz. The CM angle, ventilation load, explains hardware you'll otherwise wonder about on the drawings. Energy recovery ventilators that use exhaust air to precondition incoming air, dedicated outdoor air systems. Demand-controlled ventilation with CO2 sensors that throttle outdoor air to the actual crowd instead of the design crowd. All of it exists because of the two formulas on this slide. Outdoor air is expensive, so an entire product industry exists to make it cheaper. And infiltration is the reason air barrier details, door sweeps, weather stripping, and vestibules at main entries are in your specs. A vestibule is a cooling load device. It keeps a 100-degree gulp of parking lot air from walking in with every customer. When the punch list says the building can't hold humidity, leaky envelope and propped open doors are suspects 1 and 2. We've built the load in BTUs per hour, envelope, solar, people, lights, plugs, outdoor air. Now the unit the entire industry actually talks in, the ton. 1 ton of cooling equals 12,000 BTUs per hour. Where's that from? The ice trade. The cooling delivered by melting 1 ton of ice over 24 hours. The ice wagons are long gone. The unit stuck. A 5-ton rooftop unit removes 60,000 BTUs per hour. A 400-ton chiller plant for 0.8 million. Quiz alert. 1 ton of refrigeration equals 12,000 BTUs per hour. This is the number of the day. Total BTUs per hour divided by 12,000 equals tons. It will absolutely be on the quiz, and you'll use it for the rest of your career. So our 40-person classroom from earlier, 18,000 BTUs per hour of body heat. Divide by 12,000. A ton and a half of AC, just for the people. See how fast the vocabulary becomes useful? Now, rules of thumb, the estimator's early phase tool. For typical office buildings, figure 300 to 400 square feet per ton. Take a 40,000 square foot office. At 350 square feet per ton, roughly 115 tons of cooling. That's a real, usable number for concept level pricing. Checking whether a mechanical budget is sane, sanity checking a bid, sketching an electrical service. Denser, hotter occupancies run heavier. Restaurants and assembly spaces can push down toward 150 to 250 square feet per ton because of the people and the kitchens. Data spaces are in a category of their own. Milder load buildings, warehouses with spot cooling, run far lighter. Quiz alert. Rule of thumb for offices, roughly 300 to 400 SF per ton. Know it, and know its place. Rules of thumb are for conceptual estimates and sanity checks, never for final equipment sizing. Real sizing comes from the load calculation. 2 more ideas from this slide finish the picture. Peak load. Equipment is sized for the design peak. That mid to late afternoon moment when the west sun, the outdoor temperature, and a full building stack up. And the design outdoor condition itself isn't the record heat ever measured. Engineers size to a statistical design temperature that's exceeded only a tiny fraction of the hours in a typical year. On the handful of freak afternoons above it, the building drifts a degree or two, and that is by design, because chasing the last degree of the record heat wave means paying for capacity that sits idle 8,758 hours a year and, as the next slide will show, actually makes the building less comfortable the rest of the time. Diversity, Part 2. The whole building never peaks all at once. East rooms peak in the morning, west rooms in the afternoon. The conference room is full at 10 and empty at 2. So the block load, the whole building's simultaneous peak, is less than the sum of every room's individual peak. That's why the room-by-room numbers on the schedule add up to more than the chiller. Nothing's missing. That's diversity, engineered on purpose. And now when a superintendent squints at the schedule and says the numbers don't add, you'll be the one who knows why. Hands-on mini problem. You do this one, 7 minutes. Calculators out. You're doing this one solo, and it uses 4 of today's constants back-to-back, which is exactly how the quiz will use them. Write this down. A small fitness studio. 30 people working out. Because they're active, carry each person at double the seated rate. Call it 900 BTUs per hour per person, total. Ventilation, 20 CFM per person of outdoor air. Design day, 95 outside, 75 inside. And the outdoor air is running 35 grains wetter than the space. 3 questions. 1. The people load in BTUs per hour. 2. The ventilation load, sensible and latent, separately. 3. Those 2 buckets combined, converted to tons. For minutes, go. All right, check it together. People, 30 times 900, 27,000 BTUs per hour. 30 exercisers heat like 60 office workers. Occupancy type matters as much as head count. Ventilation airflow, 30 people at 20 CFM is 600 CFM. Sensible, 1.08 times 600 times a 20-degree delta, 12,960. Latent, 0.68 times 600 times 35 grains, 14,280. And there it is again. The moisture load of that outdoor air beat its temperature load. Add the buckets. 27,000 plus 12,960 plus 14,280 is 54,240 BTUs per hour. Over 12,000. Right at 4.5 tons. And notice we haven't touched the roof, the walls, the glass, or the lights yet. People and their fresh air alone bought 4.5 tons. That is why assembly and fitness occupancies size around bodies. And if your numbers landed anywhere close to mine, you can officially do cooling load math. Here's the counterintuitive lesson of the day, and I need you to actually believe it, because your instincts will fight you. Bigger is not safer. With air conditioning, oversized equipment makes a building worse. Everybody's gut says pad it. When in doubt, round up a size. Nobody ever got fired for too much AC. Here's what actually happens when a unit is significantly oversized. Short cycling. The oversized unit slams the thermostat down in a few minutes and shuts off. Then the space warms, it slams on again. On off, all day. That start-stop pounding wears the compressor. Starts are the hardest thing a compressor does. So this safe, oversized unit often dies younger than a right-sized one, on top of running less efficiently and swinging the temperature instead of holding it. And the killer in our climate, it stops dehumidifying. Latent removal, the water pouring out of that condensate line, only happens while air is moving across a cold coil, and the coil needs sustained runtime to get cold and stay cold and keep condensing. An oversized unit satisfies the thermostat so fast the coil barely gets going. Temperature, handled. Moisture, barely touched. Result, 72 degrees and swampy, cold and clammy at the same time. And the occupants respond by cranking the set point down, chasing comfort with temperature because the machine won't give them dryness. Higher bills, worse comfort, and in bad cases you're on the road to condensation and mold. The thermostat is satisfied, the humans never are. Quiz alert. Oversized cooling equipment short cycles. Rapid on-off operation that increases wear and kills dehumidification because the coil never runs long enough to remove moisture. Cold and clammy equals the signature of oversizing. Bigger is not better. This is guaranteed quiz material. So how does the industry make sure sizing is done right instead of by gut? Recognize calculation procedures, and two names to know. Manual J, the ACCA load calculation method for residential work. It's what a code official asks for when a home builder wants a permit for the HVAC. And for commercial buildings, Manual N and the ASHRAE methods, the CLTD approach we touched on earlier, and, in modern practice, hour-by-hour computer simulation that models the building through the whole design day. Different tools, same mission. Replace, we always put a 4-ton on a house like this, with actual math on the actual building. Quiz alert. Manual J equals residential load calculations. Manual N equals commercial. Both exist to prevent rule of thumb sizing and oversizing of installed equipment. Worked example. On the board, let's prove we can do this, start to finish, on a real space, because your assignment is exactly this exercise. Small office suite, 2,400 square feet, here in Central Texas, design afternoon. I'll round everything to keep it clean. Follow the buckets, not the decimals. Envelope conduction, roof, walls, glass U values worked against their CLTDs. Call it 18,000 BTUs per hour. Solar through the glazing. SHGC times the glass areas, with that west exposure doing most of the damage, 9,600. People, 12 occupants at 450 each, 5,400. Lights, 2,400 square feet at 1 watt per foot is 2,400 watts, times 3.412, about 8,200. Plug loads, computers, monitors, the breakroom fridge, diversified, 6,000. Ventilation, 12 people at 15 CFM each is 180 CFM of outdoor air. Sensible, 1.08 times 180 times 20 equals about 3,900. Latent, 0.68 times 180 times 30 grains equals about 3,700. Add the buckets, right about 54,800 BTUs per hour. Divide by 12,000, 4.6 tons. You'd talk to the engineer about a nominal 5-ton unit and let the selection work settle it. Sanity check with the rule of thumb. 2,400 square feet divided by 4.6 tons is roughly 520 square feet per ton, a bit lighter than the 300 to 400 office range, which fits. It's a small suite, modest occupancy, LED lighting. The rule of thumb and the calculation are shaking hands, and that handshake is what checking an estimate feels like. And look at the shape of the load, because this is the takeaway. The sun and the envelope together are about half. The people, lights, and plugs, the inside, are over a third. Outdoor air is the rest, and a fifth of that outdoor air load is pure moisture. Change the glass, pack in more people. At a server closet, the tonnage moves. Now you know exactly which lever moved it. Still slide 9. What the CM actually does with all this, before the assignment. Let's cash today in, because I promised at the top that this is CM knowledge, not engineer trivia. So here are the 5 places this class shows up in your actual job. 1. Pricing and budget checks. Mechanical is routinely one of the largest trade packages on a commercial building, and its cost tracks tonnage. The rule of thumb plus a dollars per ton figure lets you gut check a mechanical budget or a sub's bid in about 90 seconds. If the office building should be around 115 tons and the low mechanical bid only makes sense at 80, somebody missed scope, and you just caught it before it became your problem in month 9. 2. Change management. Every one of today's load buckets is a change order trigger. Owner densifies the office layout. More people, more tons. Tenant adds a server room, dedicated cooling, new scope. Architect enlarges the west curtain wall in a design revision. SHGC, load, tonnage, duct, electrical. When a change touches people, glass, lights, equipment, or outdoor air, your antenna should go up. Has anyone told the mechanical engineer? That one question, asked early, has saved more schedules than any tool in the trailer. 3. Submittal review. When the mechanical sub proposes in or equal unit, you now know the questions that matter beyond the tonnage on the nameplate. Does the sensible/latent split match the basis of design? Same story on a glazing substitution. If the SHGC moved, the load moved. You don't approve mechanical submittals alone. That's the engineer's stamp. But you're the one who spots that a substitution in Division 8 quietly rewrote the assumptions in Division 23. 4. Coordination and real estate. Tons take up space. Tons are rooftop units that need structural support and roof penetrations, chases and shafts, ceiling cavity for duct, screen walls the city makes you build, and electrical capacity. Cooling is usually the biggest single driver of a commercial building's electrical service size. When you fight for ceiling space in a coordination meeting, you're fighting about consequences of the numbers we ran today. 5. Closeout and the first summer. The building gets tested against these loads its first August, not at substantial completion in March. Commissioning, test and balance reports, and functional performance tests exist to prove the installed system actually delivers the calculated capacity. A CM who understands the load reads a tab report as evidence instead of paperwork, and when the first hot room call comes in, starts with the smart questions. West exposure? Occupancy as designed? Outdoor air balanced? Doors propped? That CM closes the complaint in a week. The other kind sends the mechanical sub back 4 times to check the freon. Be the first kind. Stay seated, assignment details, and I'm going to walk you through it so nobody burns an evening confused. Today's participation assignment is a cooling load worksheet, posted on Canvas after class, due before next class. You're doing exactly what we just did on the board, on a small commercial space I give you. The handout has the floor plan sketch and a data table. Envelope areas with U values and design temperature differences. Glass areas by orientation with SHGC-based solar gains, occupant count, lighting power density, plug load allowance, and the outdoor air CFM. Here's the structure I want, and I'm telling you now because it's how the points are distributed. Step 1. Build the load by bucket. 6 labeled sections. Envelope conduction, solar gain, people, lights, equipment, ventilation. Show the formula, the numbers in, and the BTU per hour out for each. The people row, occupants times the sensible rate plus occupants times the latent rate. I want to see both flavors, labeled. The lighting row, what's times 3.412. Show the conversion, don't just write an answer. The ventilation rows, the 1.08 formula and the 0.68 formula, separately. Step 2. Total it, split it. Total BTUs per hour, and the sensible/latent split, 2 subtotals. If your latent line is 0, you skip the people and the outdoor air moisture, and that's the number 1 error on this assignment every semester. Step 3. Convert to tons. Total over 12,000. Round sensibly and say what nominal size you'd carry. Step 4. Sanity check. Square feet divided by tons, compared against the rule of thumb range, with 1 sentence on whether your answer is reasonable and why. That sentence is worth real points. It's the difference between calculating and estimating. And step 5, the short answer. 2 or 3 sentences on why the engineer should not just bump your answer up 2 sizes to be safe. You have everything you need for that answer on the oversizing slide. Write it like you're explaining it to an owner, not to me. Plain language. Common ways to lose points. Learn them now. Using R values straight in the equation without flipping to U. 1 over R, always. Forgetting 3.412 and treating what's like BTUs. Leaving out the latent loads entirely and dividing by the wrong constant at the end. It's 12,000, not 1,000. Show your work on everything. A right answer with no path gets partial credit at best. Because in this business, a number nobody can check is a number nobody can trust. And the daily quiz. Next class opens with the quiz on today's material. Every quiz alert is fair game. The short list to drill on the drive home. Sensible versus latent. Q equals U times A times delta T and U equals 1/R. SHGC. West glass. 3.412. 250 plus 200 per person. 1.08 and 0.68. ASHRAE 62.1. 12,000 BTUs per hour per ton. 300 to 400 square feet per ton. Short cycling and dehumidification. Manual J versus manual N. Do the worksheet tonight and the quiz will feel like a warm-up lap. Rapid fire quiz review. 6 minutes. Whole room. Last thing before the wrap. Let's rehearse the quiz right now. Rapid fire. Whole room, answering out loud. I ask, you answer, I confirm. No notes. If the room goes quiet on one, that's the one you study tonight. Heat that changes air temperature? Sensible. Heat carried in moisture? Latent. Total cooling load equals? Sensible plus latent. The conduction equation? Q equals U times A times delta T. And U in terms of R? 1 over R? So in R, 20 wall has a U of 0.05. What does CLTD stand for, and why does it exist? Cooling load temperature difference. It replaces plain delta T to account for solar heating of the surface and thermal lag. The fraction of solar energy that makes it through the glass. SHGC, solar heat gain coefficient. For summer cooling, you want it high or low? Low. Worst window orientation in a Texas summer? West. Why can't an overhang fix west glass? The afternoon sun comes in too low. One seated person adds roughly how much heat, and in what mix? About 450 BTUs per hour, roughly 250 sensible, 200 latent. 1 watt of lighting becomes how many BTUs per hour? 3.412. Where does the rest of the lighting energy go? Trick question. There is no rest. All of it becomes heat. The commercial ventilation standard? OSHRI 62.1. Sensible load of an airstream? 1.08 times CFM times delta T latent? 0.68 times CFM times delta grains. 1 ton of cooling equals 12,000 BTUs per hour. Office rule of thumb. 300 to 400 square feet per ton. Is a rule of thumb acceptable for final equipment sizing? Never. Conceptual estimates and sanity checks only. What does an oversized unit do all day? Short cycles. And what job does it fail at? Dehumidification, cold, and clammy. Residential load calc method? Manual J commercial? Manual N. And the concept that explains why the building's total tonnage is less than the sum of the rooms? Diversity. That's the quiz. People, you just took it. Anything that didn't come out of your mouth automatically. That's your 15 minutes of study tonight. Wrap up. Big picture before you go. A cooling load is just an inventory of heat, where it sneaks in and where it's born inside, priced in BTUs per hour and paid for in tons. You now know every account in that inventory. The envelope, the sun, the people, the lights, the plugs, and the air itself. And you know the air brings a hidden water bill with it. You know why the machine that's too big to fail fails at the one job Texas needs most. And you know the names of the methods that keep the industry honest. Next class, we take these tons and turn them into actual systems. The equipment and distribution that deliver this cooling. So today's numbers are the foundation for everything that follows. Assignment tonight, quiz next class. Go find a condensate line dripping somewhere on campus this afternoon and appreciate it for what it is. Latent load, leaving the building. See you next class. End of class 6 script. Approximate total runtime. 80 to 85 minutes at lecture pace, including the board example and assignment walkthrough.